we're going to take a look at how we figure out the rate law of a reaction. So let's first take a look at what the rate is. A rate is the negative change in concentration of a reactant over time, or the positive change of product over time. The sign changes because rates are always positive, and the amounts of reactants disappear over time, and the amounts of products increase over time. So let's take a look at this reaction. I have 3 hypochlorites breaking down into 2 chloride ions and a chlorate ion. And I'm going to set up a little chart like the charts we've seen before. And I know that at time 0, I have 0.12 molar. And after 100 seconds, I have 0.9 molar. So I can calculate my change. And based on stoichiometry, that's also the change. I can calculate the change for the other two. Now in earlier problems, what we've concerned ourselves with is what is it at the final? And I can calculate those. If I start with 0, I add 0.2 molar, it's 0.2 molar. If I start with 0 and add 0.1 molar, it's 0.1 molar. But now, our big focus is the change. This is what we're concerning ourselves with. So the rate of disappearance of hypochlorite is the change in concentration over the change in time. Always final minus initial. And so we end up with a rate of 0.0030 molarity per second. For chloride, it's 0.2 molar per 100 seconds. Our rate is 0.0020 molarity per second. And chlorate is 0.1 molar per 100 seconds. Now, which one is the rate of reaction? By definition, the rate of reaction is the one where the coefficient of 1. So this is my rate of reaction, 0.0010 molarity per second. Rate of reaction might be in the stoichiometry, it might not. You have to pay attention to the equation. Now, how do we figure out what the rate law looks like? We're going to use something called the method of initial rates. And so for any reaction, the rate law is the constant times reactant to a power. And that power is called the order. So for the example down here, if the rate is K times A to the second power, that means doubling the concentration quadruples the rate, and it is second order in A. If it's B to the first power, doubling concentration doubles the rate, and it's first order with respect to B. And what we want to find are these exponents, x and y, and the temperature-specific K. The x and y are for the reaction. The K is for the reaction and the temperature. And the only way we can do that is an experiment or a series of experiments. And we're going to use a series of experiments called initial rates. So here's what it looks like. We want to measure the rate at the beginning of a reaction. And we're going to compare the concentration to the rate just at the fastest part at the beginning. So what I have outlined here is the reaction we're going to look at. We have thiosulfate reducing the iodine molecule. So we have thiosulfate in there. Thiosulfate's not a reactant or product. No, we've added it to create the color change. So here's my equation, but thiosulfate is what we're going to use to see. So we can see that the hydrogen peroxide is a different chemical, so it's slightly different, but we're going to do the reaction about the same way we've been doing it before, and it will show you we're adding one set, and now here's the other set of chemicals. The thiosulfate, which we'll use to change color, and the potassium iodide, which is part of our reaction, and the starch, which we're going to use as an indicator when the reaction is done. And you can see that they make solutions, and we'll see them mix the solutions together. And it looks like nothing until all of a sudden it looks like everything. And there's the color change. Clock reaction, it looks like nothing's happening until something does. But we're measuring just this part right here, the beginning of the reaction. So what's happening here is the iodide is turning to iodine, but then the thiosulfate's turning it back, and the bromate's turning it back, and the thiosulfate's turning it back, until we run out of thiosulfate. The actual chemistry is not all that important. The key is this lets us find the initial rate. Change in bromate over change in time. So to do that, I did the first one. I took the change in bromate, 6.7 times 10 to the negative third, to 0, over my change in time, 171 seconds, and divided. So pause the video and do that for the next 3. So here are the results I got. These are the rates we're going to use for the rest of the experiment. So to find the rate law, we're going to compare 2 trials. And you want to pick 2 trials that have one thing different and 2 things the same. So to do that, we're going to compare trial 2 and trial 1. So I wrote the rate law. Rate equals K times iodide concentration to the X times H plus to the X times bromate. Sorry, H plus to the Y to bromate to the Z. And I did that for experiment 1 as well. Why did I put 2 over 1? Because I like my rates to be, my rate ratio to be over bigger than 1 because I hate fractions. If you do it the other way, it works just as well. You just have fractions. If we solve this, we see that this cancels out, K cancels out, and 3.1 is 2.9 to the X power. X is to the nearest whole number 1. And it's typically going to be a whole number. Sometimes it's a half. To find Y, I'm going to do this with trials 1 and 4. So for trials 1 and 4, I have my rate that I calculated for 4 and rate for 1. Divide those and I get 9. My K's will cancel out. My 0.0017s cancel out. We now know they're to the first power. This becomes about 3. And my last fraction cancels out. So I end up with 9 equals 3 to the Y power, approximately. So Y is going to be 2. And I repeat that step for trials 3 and 1. I divide my rates and I end up with close to 4. My K cancels out. My iodide cancels out, and we now know that that's a 1. My hydrogen ion cancels out, and that we now know that that's a 2. And we end up with 2 to the Z power is about 4, so Z is 2. So now I can write my rate law. Rate is K times iodide times hydrogen squared times bromate squared. That is not related to the stoichiometry of the reaction, but it is related to the mechanism. Now I need to find K. Well, that's pretty easy because I now know rates and concentrations and their powers. So I just pick one rate and I plug it in, and I solve for K. And I can do that for a second rate. And I should do this for each and every experiment, and what I find when I average them together is that K is 1.8 times 10 to the 6th, molarity to the -4th power, second to the -1 power. And now I can use it to find the rate of reaction for any set of molarities. So now I know that my rate is my rate constant times my iodide to the 1st power times my hydrogen ion to the 2nd power times my bromate to the 3rd power, and that gives me how fast it's going. Pause and try the second one. All right, this is what I ended up with. Now, going back to the beginning when we talked about the stoichiometry of the reaction, bromate is a 1-to-1, so the rate, the disappearance of bromate is the same as the negative rate of the reaction. The disappearance of iodide is 6 times faster. I took my rate times 6. And the appearance of iodine is 3 times faster than my rate of reaction. We get that from the stoichiometry. Now it's your turn. Try the problem at the end of the packet, and you'll see the answer key posted in Canvas. If you have questions, let me know. Good luck.